welcome everyone to another edition of the Finite Element Seminar at Lawrence Livermore National Lab. Today is my pleasure to introduce Patrick Zulian. Patrick got his degree at the University of Lugano, and got all his degrees at the University of Lugano and still there. He's a group leader in the Euler Institute there. I really like the name. And he's been at Livermore several times. Long time ago, I want to say 2018 or something like that, 2016. And he's done some work also in FEM with his monolith library, if you're familiar. He works on parallel domain decomposition, multiphysics problems, a lot of interesting stuff that's relevant to the FM community. And today he's going to tell us about Immersed Domain Approach for FSI, or fluid structure contact interaction, also interesting for us. He's calling us from Switzerland. We really appreciate that. And thank you for coming and presenting, Patrick. The floor is yours.
Thank you, Sanyo, for the very kind introduction and for the opportunity to talk at this very nice event. So this work is a joint work with several people, as you can see by the names, but let's say the main collaborators that contributed to the work that you're seeing now are Maria Nestola, Fabian Vermellinger, Luca Mangani, and Rolf Krause. I'm going to talk about immersed domain approach for fluid structure in contact interaction, and I will go back and forth with different topics, also subtopics around this. Okay, so this is a bit the idea of the talk is I will talk about something simpler. So I will start with flow and transport in fractured porous media, and I will expose the techniques there, and then the same techniques will be also used for contact and also for fluid structure interaction. So the whole idea of immersed fluid structure interaction is that you have an independent grid, like a background grid, which is not visible here, and you have some elastic structures which are immersed in within this grid, which are meshed separately, and you have a full coupled simulation where there is an exchange of forces between the solid and the fluid. And we will see how we do this in this talk. But first, we talk about fractures, and particularly where you can represent fractures. So we said we do immersed stuff, but there is also the other option, which is going for fitted or decomposition. So we see on the left the embedded approach, where we immerse either lower dimensional fracture, like here, or an equidimensional fracture in a background mesh. And as you can see, the meshes are independent from each other. So this is a convenient way, particularly for this application, is that you can generate many fracture networks, and you don't have to deal with the meshing stage as you do for the other way, which is the fitted decomposition. Here, the interface or the fractures are captured exactly in the background mesh. And as you can see here, also at the interface, the mesh don't have to match, but at least the geometry of the fracture needs to be captured exactly. So this is a nice accuracy. However, all the complexity falls into the meshing stage, which sometimes is not feasible because you have things moving and so on. So here is the simplest problem I can come up with, and it's a simple flow problem, a Darcy flow problem, and we define it in a domain omega and a fracture gamma, and we want to solve the problem for the pressure, so the pressure in the background and the pressure in the fracture, and we have some source and sink term, and then we have a Lagrange multiplier, which we use to enforce some continuity of the pressure. Then there are the typical permeability tensors, and the weak form would look something like that. So you have a variational formulation of the equation inside the background mesh, and you have the same but in the fracture, and then you have some coupling term which are which are enforced through a Lagrange multiplier, and we enforce also these so-called weak equality conditions. So these bracket operators are L2 scalar products, and we want the pressure to be the same in the intersection between the fracture and the background matrix in a weak sense. So they have to be, the weak equality condition has to be satisfied for all Lagrange multipliers. We do finite elements, and I guess it's the right place to talk about finite elements. So we use standard Lagrange elements. In this case, we either use tetrahedral meshes or hexahedral meshes, or the 2D equivalent of that. And we typically choose the Lagrange multiplier space on the fracture mesh, such that the mesh of the Lagrange multiplier and the pressure is the same, but we can choose a different space. So if you do the typical expansion of the finite element function as a series of coefficients and basis function, we can construct the pointwise algebraic equations. Typically, in our simulation, we have a particular choice of Lagrange multiplier, and this Lagrange multiplier satisfies the bi-orthogonality condition, which is here. So pretty much is some kind of enforcement of a mass lumping. But it also has to satisfy positivity, which is only an issue when you're doing second-order elements, but there are tricks to go around this. And once you have this bi-orthogonality condition satisfied, then you can assemble the various pieces of the equation. In particular, this D will be a trivial matrix that is trivially invertible. Most of the time will be just a diagonal matrix, and some other time will be a composition of two matrices that are trivially invertible. And we have, this way we have our saddle point system, and you can see the first row, it's our background problem with the coupling term B, and here we have the fracture problem with the coupling term D, and then we have the equation for the Lagrange multiplier, which is what we said is the weak equality condition. If D is trivially invertible, then we can, on paper, we can already do an inversion of D and compute explicitly this, this transfer operator T, which then allow us to do some kind of static condensation of the linear system. So we can eliminate two of the variables and solve only for one of the variable. And the nice thing about this, particularly for this problem, is that we go from a problem that is a saddle point problem to something that is symmetric positive definite. It can be solved with standard algorithms such as CG or multigrid. So, okay, so the one of the main ingredients for constructing T is the quadrature. And in order to compute this quadrature, we need to first detect intersections like here or like here. And depending on the type of intersection, we might do different things. So if it's a surface coupling, we might have to do some surface normal projection, particularly for contact. If we have a volume coupling, then we have to compute some volumetric intersections, so some polyhedron, and then of course 2D, it's much easier. Once we have this intersection, we can mesh this intersection and map the standard quadrature rules to the meshed intersection, and then apply the inverse geometric map to evaluate our so-called mortar integrals. And we can do with all type of combinations of polyhedron segments and so on. And I'm going to show some results that are taken from these two papers. And they are very simple benchmarks, which are typical in this type of fracture simulations. So we have a regular fracture network, And we have two benchmark cases. One is for conductive fracture, and the other is for blocking barriers. And typically with the Immersed method, you cannot solve this. So these blocking fractures cannot be solved with the Immersed method. In fact, we can only go for the conductive fractures. And for the blocking fracture, instead, we go for a decomposition approach such that we can capture the pressure jump or the discontinuous pressure jump here by exploiting the difference in resolution we can have inside the fracture and outside the fracture. And you can see from these plots that we are in line with other methods in the literature, and we have the same convergence rates as the other methods in the literature. And most of them are not immersed, so we have the advantage of being more flexible. And of course, if you go for a decomposition approach, you will have immediately a much lower error because of the geometry. But at the same time, you will have to have much more DOFs, much more degrees of freedom. And the condition number is typically higher. So when we look at the condition number, of course, we are interested because we want to make the life as easy as possible for our solvers or for our iterative solvers. And we try different types of Lagrange multipliers. So if we go for the bi-orthogonal basis, which we call the dual Lagrange multiplier, then we can eliminate the saddle point system, and then we can have much lower condition numbers from the start. And this makes it a bit easier to solve the system. But we can also choose other Lagrange multipliers if we want a more regular or more smoother Lagrange multiplier. We can also do that. We tried also a higher order and so on, and but we do all our simulation with low order now. And so here is a bit more interesting example, maybe. It's a higher resolution example in 3D. And for that, we need, of course, two different meshes. So here still high resolution compared to the rest. But the two meshes are independent from each other. So we can measure fracture network and then immerse it. And we can obtain this pressure from the simulation. You can see here that fine level detail is captured quite convincingly where you have the fracture. And once we have the fracture, once we have solved for the pressure, then we can solve some transport problem, and we can have some concentration going through the to the fracture network and the porous media. So since we are moving towards something that looks more like a fluid, then we can take the same idea and apply to a bit more challenging scenario, which is fluid structure interaction. In some cases, also with contact. We have developed three different technologies for this. One is AV flow, where we did some collaboration with University of Bern, and we use it for Hartwald simulations. They implemented the fluid dynamics, which is based on finite differences, high-order finite differences, and we do the coupling using an immersed boundary approach. While for the other two technologies, so one, I think we discontinued it, which is this one, but we still have some results to show. We do finite element and finite element, and we use the method of Lagrange multipliers for solving the contact problem. And then the most recent application is liquid diaphragm pumps, which is done in our Fluya code, which is at the moment closed source, but will be open hopefully in the next, I would say, months. And this is a control volume finite element code, and is using an immersed domain approach. And for the contact, we use a shifted penalty approach, and this is still a work in progress. So again, for fluid structure interaction, we find ourselves to decide if we want to go for a boundary fitted method. And for FSCI, the standard method is arbitrary Lagrangian Eulerian. Here, the fluid mesh deforms with a solid mesh, and has really accurate results at the FSCI interface. But for the type of simulations we are doing, we really need large deformations and large displacement, which eventually will lead to distorted fluid grid. And then there are sort of things that we need to do to make sure that the simulations can go on, and this has some effects also in stability and accuracy. So we say, okay, let's throw some things out of the window, and then let's go directly to immerse techniques. And of course, by going to immerse techniques, then the FSCI interface will not be captured as good as the previous method. And in order to compensate for that, we need a high resolution, right? So a high resolution is a requirement there. We cannot solve anything useful with small problems. But at the same time, it makes it easy to separate the two physics, the fluid and the solid, and in particular the fluid physics, which is quite challenging, and we can have different solvers there. We can go from finite element, finite volume, control volume, finite element, or finite differences, or all sorts of things. Also, discontinuous Galerkin, if we tried, I would say. And in this presentation, we will cover the Immersed Domain Approach, which is the fluid and solid are coupled in the entire intersection volume, meaning that we ensure the continuity of the velocity in the entire overlapping region between the fluid and the solid. And this approach is constructed on top of the paper from Christian Esch in 2014. And you can see some example meshes. Okay, so this is, I guess, nothing really new. It's just the Navier-Stokes equations, and then there are some elastodynamics equation. And as before, we have some coupling term here, which is the Lagrange multiplier, and we have some equality condition here, which is marked in green. So everything that is coupling, it's in green. And this will result in the same idea as we saw before, which is the weak equality condition. Of course, in certain simulations that we have the problem that the solids interpenetrate each other, and we also have to solve some containment problem for the pumps. But for this type of simulations where we have a simulation of heart valves, we have we started with this actually. We have this interpenetration, and we would like not to have it. Also because then the coupling between the fluid and the solid, also we have some strange effects. So so we would like to handle both multi-body contact problem and unilateral contact. And we base our work on these papers by Rolf Krause and collaborators. So just to clarify a bit what contact problems, why are they challenging? It's first you have this contact boundary, which is not known a priori. And from this contact boundary, you have to identify this contact mapping, which is not known a priori. So during the simulation, you will have to figure out what is this contact mapping. And this contact mapping will eventually generate some gap function and some normal field, which is giving you the direction of these contact surfaces. And then, of course, there are the standard contact conditions, which are listed here, but I will not spend too much time on it because it's standard material. So what do we use in particular for this? Why do we use these mortar integrals for coupling conditions? So many people use standard interpolation, but if you look at the Lagrange multiplier, you see that it doesn't look that good. It looks very spotty, and I guess you can imagine that if you add this as a forcing, the results will not be acceptable or stable. So with a variational approach, you can ensure that you have at least a continuous Lagrange multiplier that doesn't create weird artifacts. And in particular, there is a whole body of literature which shows that even some basic patch tests cannot be passed by the first approach, while with this you can pass them. So you can see here the type of integral you need to compute. We already saw it in the first part of the presentation. And we do the same for the contact, actually. So the contact has the same kind of mechanism. And these mechanisms are explained in this paper from 2016. And we have a kind of general approach, which now we are working on some more specific version of it, where we do the volumetric coupling, surface coupling. and we do it in parallel. So this can scale. Actually, the whole code is also present inside MFEM. Okay, so we said that we have two applications. So the first one is with bio-prosthetic heart valves. And in this case, I'm going to present some results from our discontinued code, which is the FEM for fluid and FEM for structure. And in this case, it's a staggered approach. So we solve the two problems independently, and we solve for the mechanics, including contact, and then we compute some velocity out of the solution. We transfer the velocity, we impose the velocity in the fluid, we compute the solution of the fluid and the reaction force, and transfer the reaction force, and we iterate multiple times until the solution or the Lagrange multiplier doesn't change, let's say, up to some numerical tolerance. And so this is a staggered approach. So again, it's interesting because you can use specialized solvers from one physics and the other. And in that direction, we are working on a substructuring, non-smooth substructuring method for contact that we will be using in situations like this. And so what type of applications you can look at with this type of software? We created some toy problem around the idea of bio-prosthetic heart valves. And these bio-prosthetic heart valves are actually a prevalent valvular pathology in the West, particularly. And it's due to, so this aortic valve stenosis is due to a progressive thickening of the valve. And you have some let's say, severe impairment of the motion. And typically, it's when degenerates too much, needs to be replaced. And when you're designing a replacement, maybe you would like to test the durability and performance of the replacement. And it's better to do it maybe with a simulation. So in this direction, we created two different models, so two different models of the bioprosthetic heart valves. And within these two models, we had like isotropic version of the material, and also some material with fibers, so anisotropic, as you can see here. And we try to do some simulations and see how the material reacts to a certain forcing. In this case, is only mechanics, but we can already see that the second model doesn't work that nicely. So you have all these higher stresses where you have the stent, which is the attachment of the leaflets of the valve. While for the isotropic, it's a bit lower, but still there are certain concentration here. While for the fiber version, the fiber reinforced version, the stresses are a bit nicer. And of course, we want to test also the hemodynamic performance. So we did some experiments, and more details can be found on this in this paper. But we think this is a nice, let's say, a nice example of something that could be eventually used in the future. More recently, though, we moved to something more completely different. So from biomedical problems, we moved to some industrial scenarios. So we have a collaboration with the industry and are interested in designing liquid diaphragm pumps. And here everything becomes even more challenging. I mean, the sub-problems are challenging on their own, but here you have the combination of both. And you have stuff like blockage of fluid. So you have like complete, like very, very steep transients in the simulation where the fluid is blocked. We have complex geometries. We have physical parameters for the engineering goals, which are quite, tough. And then, of course, is a transient simulation, so we want to capture all the dynamics convincingly. Also, when we developed this code, we were under a certain timeline, and we had some restriction, so we had to make certain design choices. And I can show you one example of such simulation, which is this. The entire pump geometry is hidden because we have to censor some of the results since the company decides what to show or not. But you can see, for example, here, the valve is pushed against the invisible pump that is here, and you have this really aggressive deformation in this simulation. And this whole simulation is driven by a piston that is down here that moves the elastic diaphragm, and all the fluid motion is pretty much driven by the pressure in this chamber. So here the idea is a bit different from the other algorithm. In this case, what we do, we have this control volume finite element for the fluid, and every time step, what we do, we assemble this coupling operator, so this matrix T. We detect and assemble contact matrices and vectors. So this is done only once per time step, but the time steps are not so large, so we can still keep it accurate enough. And then we linearize the fluid and solid, and we penalize the contact inside a Newton method. We condense the system, we solve the linear system with some algebraic multigrid, and then we have the solution. And the system we solve is very similar to what we saw before. It's a saddle point system, and we use the same idea as before. If we have the dual Lagrange multipliers or this bi-orthogonal basis, then we can invert D, and then we can eliminate the velocity of the solid, the Lagrange multiplier, and we can only solve for the fluid velocity, as shown in here. And then once we solve the linearized system, we have the velocity increment of the fluid, and we can transfer it to the solid, and we can recuperate pretty much all the necessary quantities to linearize again. So it's a full implicit solve, and it's a monolithic, completely monolithic solve. For the contact is pretty much contained inside a force, and it's also contained inside the Hessian, which I probably forgot to put here. And we tried different types of penalization. We went from interior penalty, logarithmic barrier, and so on, or even we tried some polynomials. And we ended up doing exterior penalty and the shifted variant, which is a so-called shifted penalty method. And why do we do the shifted penalty method? Is because we want the kind of ease that comes with a penalty method, but we want also the accuracy that is typically only given to non-smooth technologies. And you can see an example here. So if we use the standard penalty method, even once you converge with your nonlinear iteration, we will have some penetration, which is clearly visible with the naked eye. And you can see it also here, which is like 10 to the minus 3. But with the shifted penalty, you can kind of correct that. And one way of seeing it, which is very wrong but very intuitive, is that we change the obstacle pretty much. And by changing the obstacle, we solve a different problem, but then we have an interpenetration of 10 orders of magnitude lower. So this makes it nice because we have the flexibility, especially if you have some embedded constraints, which is what we have in our monolithic solver, to solve the contact together with the rest of the system, linearized system. And but before even we start simulating, we need to figure out the initial conditions. So before the simulation, we need to perform another kind of simulation where the goal is to take the CAD models that we receive from the company and put it in a scenario where we can actually simulate something. And in order to do that, we have to get rid of all the intersections between the valves and the pump geometry, which is at rest, the valves are intersecting all over the place. So in order to do this, we use a sign distance field, in a specific section of the pump geometry, and on a structured grid, and then we sample the sign distance field in the solid mesh, and we solve an unilateral contact problem given this sampling, and then we repeat several times. We resample and we solve, we resample and solve until we converge to a fully contained geometry, which gives us a pre-stressed material. So it's already very stiff material, and it's pre-stressed, so it's going to want to go back to its original configuration. But this is the initial data or the initial conditions for the solid part of the fluid structure interaction or contact interaction simulation. So this is why we also need to take care of the contact inside the fluid structure contact interaction simulation. And so we are working on an article, but for the time being, I can show you already some results. So we had the luck to access this test rig. So this is a real life test rig, and they have it at the KNF Lodos in Switzerland, and it's pretty much a pump, but it allows to measure the valves displacements, which are here very small, through a laser. So this plexiglass window, you can measure the valve displacement, so you can know something about the dynamics or the elastodynamics of these valves. And you have the piston here, and you have some valve limiters, which are very small, but they also will go in contact. So the valves will also go in contact with that when they deform too much, but they also will go in contact with the casing, so where they're going to be attached, so the so-called valve seat. And of course, we started with a very coarse simulation to see if we can somehow reproduce at least the measured deflection of this valve, the displacement of these valves. So we did some modeling assumptions on the model. Particularly, the piston has been modeled as an inlet-outlet boundary condition. So the water reservoir, which are above the pump, are modeled with some opening boundary conditions, and the valves are modeled as immersed solids or immersed elastic bodies using the Immersed Domain Approach. And this is kind of a very coarse result. But you can see the pressure stroke and the suction stroke, and you can see once the valve is closed, no more water is going through, and this is fully open, and the water can go through here. And we compare the measurements with the simulations, and even with such a coarse resolution, we kind of were able to capture, let's say, the macro scale dynamics of the valve, and we had much more simulations, but we cannot show them. So so from this part of the pumps, I'm done. So now I will give a shout out to some of the people that use some of our technology. So one of them is Pascal Corso, which took the AV flow code, which was the one with finite differences and finite elements, and did some nice experiments. So he did some validation by comparing the simulation to real-life experiments, and was able to show quite convincing match between the simulation and reality. Here there is no contact though, and the valve geometry has been modeled in such a way to avoid contact, so it's an older effort. But you can still see that if we compare certain measurements from the simulation to the experimental data, we can achieve quite a nice matching. And I think I can show some movies. I don't know if Pascal is here, but in case if you have any questions, you can ask him directly. So in this case, he used the code to test different valve designs, and then he looked at different metrics such as vorticity and so on. And he can it can understand based on different simulation which vial design performed the best. And he did also an additional study, always using our code, which is on predicting calcification of these leaflets, which is what drives problems like stenosis and so on. And this is all work that he published. And if we maybe find the result. So, and in this case, he managed to come quite close in terms of predicted calcification by, of course, extending what we did with his own models and so on. And here is another simulation. In this case, he's trying to see what stenotic heart valve is performing, the helical structures, the vertical structures, and here is the jet. And he compared that to different valve designs. Since I'm not the expert here, I will just refer you to Pascal if you have any questions. So we also use the same techniques to do some contact between rough surfaces in geophysical applications. And in this case, it's just surface contact. There is also another work by von Planta where he took these results and then performed an FSCI simulation on top of it, always using our code. And then we did also some work at Lawrence Livermore, where we used these variational transfer techniques, which is in FEM, to do some spatially colorated random field sampling using non-matching meshes. Here we want somehow the boundary to be far away from the sampling region. And this is where immersed approach can also be useful in this case. And here I'm going to move to a more recent work, something that I'm working on right now. And it's all like new, so there might be some mistakes. And if you have any feedback on this, it will be very welcome. So I'm currently working on semi-structured operators, particularly because we need greater spatiotemporal resolution for our simulation. So what you saw, it's still very coarse, so we need to go towards supercomputing. And we want to do that first because we want to capture small scale dynamics, but we also want to make the physics more complex. In fact, we want to include multi-phase flows, particularly for simulating free surface flows and cavitation. And if we go in this direction, then supercomputing is mandatory. So this is why we are trying to redesign some of the components of our simulation, and particularly by using semi-structured operators. And I mean, if you're familiar with FEM, you know that if you go for higher order and everything, you can exploit GPUs much better. And this is our target hardware. So now in Switzerland, we also have this new Alp supercomputer, which is equipped with Grace Hopper's superchips. And we want to use that. And so we started trying to replicate some of the ACP results. And we were happy to see that we can outperform, this is still in our old GPU, but we could outperform like standard Q-sparse SPMV quite easily by using some matrix-free version of it. And particularly, not only higher order, which is just second order, not higher order like FEM, but second order, it's already enough to outperform the Q-sparse, even if Q-sparse is working in lower order. And we can do some, like say, low order refinement of the elements and still beat higher order, as in this case, in terms of throughput. And we took this and we see, okay, additional regularity in our data structures definitely benefits performance. So we started to go all in on this. And the natural reasoning is to first consider structured meshes, right? So we look first at memory footprint, for example, of structured meshes and go to unstructured. So why we look at memory footprint? Because even during computing, we need to store this data and we need to read this data to evaluate our operator. So this is a simple example. We we take one of the points between structured and unstructured, and we show already what we need to read once we apply an operator as simple as Laplacian. So, and this is very minimalistic. So it's just a very small operator. It's 128,000 macro elements. If you in the semi-structured mesh, which is equal to 65 million elements in the fully unstructured mesh. And we are very conservative in the way we store our operator. So we just store 6 scalars for the first fundamental form of the Laplace operator, which is FP16. So it's a very small footprint, you know, on the GPU. And of course, we have the nodal fields, the elemental indices, and the coordinates, which depending on which type of geometry you use, you still want to shift them to the GPU. In our case here, we assume that the elements are affine, so one fundamental form is enough to capture the geometry for a simple Laplace operator. And you can see, of course, for a structured mesh, then there is no overhead, pretty much it's virtually zero. And for an example like this, the memory footprint is like half a gigabyte. If you go for unstructured, then we're already at 4 gigabytes. So if you extrapolate this to much larger examples, then this goes out of hand really quickly. And this is without matrices, right? So we want to stick to matrix free. While if you go for semi-structured meshes, we still have to pay the price of storing the elements, but since the elements are fatter, so you can have these macro elements, the memory footprint is much smaller because you avoid all the redundancy you have in the mesh. And if you don't store, let's say, the corresponding coordinates, you can save a bit more. But if you don't want to make any sacrifice in the terms of geometry, you can say spend this 700 megabytes and still be quite below everything that an unstructured mesh can give. And the operator itself, like this, is virtually zero also for the semi-structured mesh. Let's say the big stuff to read is this, and of course the vector field or the scalar field that you need to read and write for computation. And okay, so someone once told me that they don't want to use multigrid because they don't want to solve problems inside a cube. But my answer is there is, for any type of mesh, there is a reparametrization you can do to describe that mesh quite accurately. And this is something we did back in 2017, which we did a surface reparametrization. And we construct a mapping from something like this to something like that, starting from the original mesh. Of course, we don't have this in the new code, and this was too complex. So some kind of man in the middle would be an interesting way to describe this. So we have to do some more work to capture the geometry, but we have an implicit hierarchical structure which can nicely be mapped to hardware, and naturally gives rise to efficient ways to access this data for multigrid and for substructuring methods too. So if you have these subdomains that are indexed implicitly, then you can nicely do some substructuring approaches, and you can decide on the work granularity. So if you have like really huge elements, like 1 million degrees of freedom per element, then you can have 1 element per GPU, for example. That's a bit extreme, but it's something that in principle you could do. And of course, the main target is matrix-free operators, so we don't even talk about matrices at this point. And the results I'm going to show to you are not optimal by any means. They are very early results, but it's just to share some ideas and maybe get some feedback. So we try to solve something on very reduced hardware. So we implemented a multigrid for Laplace, like our first baseline. So the code is not super optimized, but we can already understand some of the things that gives us advantage for this semi-structured discretization. So one thing you can see immediately is, for example, from this table. So n, it's the number of sub-elements you have for every dimension. So the coarse level is less efficient than the fine level. So it's even if you have less degrees of freedom and let's say the time it takes to evaluate the operator is smaller. In terms of throughput, it's quite like 3 times slower. And this is done not on a GPU, but is done on a CPU on the Shaheen supercomputer on actually one node, where we solved the Laplace problem with 2 gigadofs, so with 2 billion degrees of freedom, and we measured the average throughput for every operator at every level of the hierarchy. We did the same on my Super Mac M1 Max, and of course it's a bit slower. And we did the same on Grace Hopper GPU, which is definitely much faster. But I'm quite say from different runs I did, kind of the story is always the same. So more structure, better throughput. And so with this technology, I started to try it and to work with some colleagues from PSU to create a multigrid for contact. And we worked on this multigrid by using this shifted penalty approach. There are no details in this presentation, but we will start writing the paper soon. And we can solve relatively high resolution problems with very small hardware. So on my laptop, I can solve about 150 million degrees of freedom for a contact problem. And I think on Shaheen, I can solve about half a billion degrees of freedom on one node. So the fact of using these data structures already pays off, and the results are quite convincing. If we look at the contact stresses, they look like you expect. But we were interested in something more meaningful because why do we want such a large resolution? Is because we want to solve contact problems with high frequency details, and high frequency details may be challenging for a multi-level operator. So we came up with some, let's say, tunable example. So this is a surface which has different frequencies, so you can create any surface with any type of frequencies here. And this is stored as a sign distance field. And we solved a problem with the cube, or half a cube, in contact with this rough surface with about half a billion degrees of freedoms. It took a relatively long time, it's 40 minutes, but there are a lot of things that are not optimized. It's only one node, and but it's clear where we need to work. So one is the actual application of the operator and the nonlinear smoothing steps. But if you look at this number, then you can extrapolate to different architecture, right? So it's nonlinear smoothing is taking pretty much most of the time, and we are using a very basic smoother, which is block Jacobi, and still we are able to solve this problem. And as you can see, so this is the contact stress. This is like a detail of one part of the surface, and you can see that a very small part here, it's already relatively fine resolution, and we can still have, let's say, a good contact stress. There is a, let's say, a numerical error to 10 to the minus 9, but I think it's expected since it's not, so it's a shifted penalty approach. So you still have some really small error. And in the direction of GPU and so on, we started also looking at how to resample things a bit more efficiently for our transfer operator. And we started, as usual, from structured meshes and moving to unstructured. And we try to see if we can do some structured to unstructured resampling efficiently. So this is some work that Simone Riva-Tusi is doing. And it's based on the premise of this paper by Boffi and others, which shows the effects of approximate quadrature in terms of convergence rate. So you can still not do the two projection exactly, but you can still have some decent convergence rates in terms of error. So we tested both first order and second order elements, and we started doing this on Shaheen, on the supercomputer at KAUST. And we look at the say strong scaling or speed up by increasing the number of resources. So if I'm not wrong, these are just four nodes of the Shaheen, but we can reach something around throughput of this resampling for linear tetrahedron, which is around 200 megadofs per second, and which is equivalent to something around 63 giga quadrature points per second. And if we move to, even on CPUs, if we move to higher order, we can already see that we have a nicer speed up. So we can go from 200 to 400 almost immediately, and we have this throughput of half a gigadof per second using 4 nodes of Shaheen. And next step would be to use GPU. I will not spend time on the details here, but we have some tile partitioned quadrature. So we have a subset of the warps which are assigned for each tetrahedral element, and this is what gave us the best performance. I think the number of threads was 8 per element, the optimal one, and we can let's say Grace-Hopper GPU. It's already on the same ballpark than 4 nodes of Shaheen. But of course, you can see that by increasing the number of GPUs, we can speed up the computation. We still have to figure out the MPI part a bit better because it's just a prototype, but this is what we have right now. So I guess I'm at the end of the presentation. So I thank you for your time and attention, again, for the opportunity to speak here. I just summarize very quickly the content. So we see some inverse techniques applied to flow in structured porous media and FSI. We saw some possible example numerical application. Unfortunately, some results we cannot show, so it was maybe a bit dry in certain parts. Most of the code that I show here, it's BSD3 clause license. Some of the things are also part of FEM. There is this branch, which is like a PR in review. So if you want to use the monolith features inside FEM, I suggest you use this branch until it's not merged with the master branch. And yeah, the future work, we want to do larger, better, and much more physics. We want to have work on matrix-free approaches for contact and preconditioning techniques, of course, for the semi-structured operator. So I thank InnoSwiss, the Swiss National Fund, UniDistance and USI for the support, and now also the new project, which is a past project, XSFSI. So thank you again.
All right. Thank you so much, Patrick.
Thank you.
Very interesting talk. A lot of things that are of interest to the FM community and folks at Livermore in particular. I'm sure there will be a lot of follow-up. Got some virtual applause already. Any questions for Patrick? Please feel free to unmute yourself and ask. Mike, go ahead.
Hi, Patrick. Thanks for the talk. I don't know if you remember, we met in Switzerland time ago. Yeah. So I think you might have even discussed this. You know, one time we tried put in the dual multipliers for coupling to the background fluid, but we did find, and I guess you have to control if the foreground mesh gets too fine compared to the background mesh, you get like the mesh locking.
Yeah.
Yeah, and I guess you really have to take care of that, otherwise you have to kind of put the multipliers on the background.
Yes, so there is actually a paper where they show for this type of approaches that there is a mesh ratio that needs to be respected. So typically, let's say in 4 words, the mesh of the fluid needs to be the same or finer than the mesh of the solid. Otherwise, you will have all sorts of instabilities and all sorts of bad effects. And the only let's say the problem with that, if you have to find fluid mesh in our case for the monolithic approach, is that the method becomes much more expensive because of the Schur complement that you compute. But typically, so it's a the immersed domain, the fluid mesh needs to be much finer or the same as the solid mesh. Otherwise, it doesn't work.
Yeah, I mean, we get problems where, you know, people would just make meshes. That's the problem when you hand this over to the users.
Yeah,
they don't respect that, and it's really hard to do sometimes. Yeah, I mean, of course there's stabilization for that, and I don't know if you took a look at some of those things, but then there's a vital vertex method where you could use on the background mesh too. I don't know if you're familiar with the method by Woolnoth and Mose, but then you can't get rid of the multipliers. So,
so
go ahead. Sorry.
The way we go, it's the way we'll go, I guess, for the next couple of developments is to get rid of the monolithic formulation and really push on the fluid resolution, because this is where you need the resolution anyway to capture all the turbulences and all the things. So it kind of makes sense for us to stick to this approach, but of course we are also ready to reevaluate if better things come along. And but yeah, so the nice thing about the monolithic approach is in terms of Newton iteration, it goes down very nicely. So that's the
I guess the easiest way to take care of it actually is if you use discontinuous Galerkin on the background.
Yeah, so we actually submitted a proposal for that. I'm not sure if it's going to be accepted. So we want to do DG for the background mesh. Also for immersed methods, DG also gets rid of this locking phenomena that you have due to this continuity condition. So we would like to do that. So hopefully the project will be funded, and then we can do that. Yes.
Yeah. Thanks a lot.
Yeah. Thank you.
All right. Thanks, Mike. Any other questions for Patrick? So is most of what you showed, is it all on simplices, or do you also simulate on hexes?
So I would say all the FSCI stuff that I showed are all on simplices, but I mean, all the current developments I'm doing, they're all on hexas, and then why I'm doing on hexas, because they're easier, and then I will try to do the same also with TETs. I guess having an implicit ordering on hexas, it's much easier than in TETs, but there is a lot of work done at FAU, which is the library high-tech, where they do nice things with stencil methods on tetrahedral meshes. So I think I mean, it's a viable approach. They also showed for CPU runtimes, they don't have it on GPU yet. They showed quite peak performance reached through this technique. So it's a hybrid stencil finite element approach.
And do you have any kind of feeling about the relative performance of hexes versus TETs on kind of similar problem?
Okay, so for the preliminary work I've done, let's say, so I see the papers that are around. So the high order stuff, it's on hexas is very good, especially the guys that can already exploit tensor cores and so on. But for, let's say, for my baseline implementations, the code I have for tetrahedra is so compact that it's really hard to beat in terms of throughput. But yeah, I plan to beat it nevertheless. So this is part of the plan. Yes.
Okay, thanks. Other questions, Mike?
Hi. In the substructuring, how did you couple the substructures? It wasn't quite clear. Like, did you mortar them, or did you use like some sort of Craig-Banton approach to reduce the order?
So it's for substructuring, you're referring to what part?
Like those things, when you back, you had the semi-structured. I guess it looks like substructuring.
Yeah, no, it's I mean, this is like standard for the moment. It's standard finite element. It's just that the storage of the mesh,
okay,
it's more efficient, meaning that
it's not just a domain decomposition approach where you're
no, it's this is purely continuous Galerkin. It's a standard finite element discretization. It's just the way you store it that makes the difference in terms of performance and also in terms of memory footprint, right? So same exact outcome, just different storage. Makes everything viable on a laptop. So I can solve, I think the largest problem I solved on a laptop for this Laplace problem was a single precision 1 billion degrees of freedom on a laptop. So you can really push it. If you push it, you can really use small resources for large number of degrees of freedom.
Thanks.
So I want to follow up on this. I mean, this substructuring looks very similar to a high order element.
Yeah, the idea comes from there. Yeah.
So I'm wondering if, but with high order, you have everything communicates to each other. So if you have a deformed, for example, hex, where all of the, I don't know, maybe you use the Jacobian only one. Anyway, I'm wondering, have you compared the performance between the substructuring and a high order that will match the same number of degrees of freedom?
No, I have not, but I mean, this is all like, last months, or I say last 2 months, I've done this, all this multigrid stuff. So I expect on the CPU to still be more efficient with the low order version. On GPU, I guess probably not, but I'm not sure actually. So the point is, so even for a mesh like this, if you're building a preconditioner, then you can sample the Jacobian of this element, for example, in the middle, and then have a very bad geometric approximation, but still be able to use it as a preconditioner. So so this is what I'm doing actually for this type of meshes. I assume these elements are affine, so then I can store, I can pre-compute certain stuff. And what I haven't done yet, but should be quite easy to do with some code generation, is to go for larger elements and then generate some stencil operators. So then you can you can pretty much optimize the way you access the memory here. You can avoid to a certain degree atomic adds and all this stuff on the GPU. We should probably make things a bit faster than I have now, which is I would say already kind of okay. If I look at the metrics that Inside Compute gives me, it's already a good place, but can be better.
Yeah. So
go ahead. Sorry.
Let me just mention something here. This is you're probably familiar. We have this way of preconditioning child operators that we call low order refined.
Yeah. So this is
essentially the low order refined grid that we do. It's uniform here. It's for us. It's the same as the degree. It will be Gauss-Lobato or some other basis for high order. But the point is that it may very well turn out to be the case that the high order operator is spectrally equivalent to the operator assembled on this low order mesh, and with additional approximation for the Jacobian, it will still be a good preconditioner for the high order. So you may be getting essentially the accuracy of high order for free. I don't know.
This is actually what we want to do. So
it's an interesting thing to try.
So on the long run, what we would like to do is higher order structures. So this will come definitely handy. Also, I'm familiar with the Pazner, right? Paper.
Yes.
And then we definitely want to do higher order fluids with DG. So this is definitely on our radar. So low order refinement, definitely something we will use. But yeah, so I'm building everything kind of bottom up now because I'm trying to figure out.
Understood.
Things from the very like small line of code to the larger line of code. So this will take some time, and then I guess there will be some lesson learned, and then I can apply them to, let's say, large frameworks. So everything I've shown here So all this code here that I've written, it's all like serial code with some OpenMP directives. So the efficiency is not, could be much better, right? So OpenMP doesn't work that well. I mean, with the same structure, it actually works better than without it, because you avoid all sorts of false sharing conditions that you have.
Yeah. I think Mike had another question.
Well, yeah, so
No comment.
I do, but probably naive. So most of you're doing everything matrix free, right? Here, for the most part. And you so that you don't have to store any stiffness terms. You compute them on the fly, right?
Exactly.
So what storage are you saving then, other than maybe the element storage? Are you saving element storage because you might need that if you have history variables and things like that?
Yeah, so I mean, my problems are very simple in terms of material, but in principle, what I store is the element indices. So these are shipped to the GPU.
Right. But you'd have Gauss points, and you might have a number of history variables. Like if you have a geological material, you have all these history variables associated with each Gauss point. You still have to save all those.
Yeah. So I guess the way I would approach it would be to have let's say one coefficient per element, I guess, and then just so if you have some material properties, I would do it per element and then just increase the resolution, right? If you do that, you still can take advantage of the higher efficiency of the operator with the semi-structured grid, right? So you can make some concessions. I don't know if you're allowed, depending on the application, I guess. You can make some concessions there, and then you pay a similar price that you pay for storing the coordinates. But for example, for the elasticity part here, I only store the adjugate and the Jacobian determinant, at least for the preconditioner, and then for the actual. So if I have like a isoparametric version, then I have to store the coordinates. So there's no way around it. And then any extra term you have to store, of course, you will have to pay the price for it. But this you have to pay the price anyway if you do matrix free. The point of matrix free is that you can do problems that on smaller hardware, I would say, that much better. So if you try to do this problem on one Shaheen node using a matrix, I think there is barely the memory to store the matrix. Then you cannot store anything else. So pretty much done with that hardware. Of course, everything is also easier with matrices, right? But
there's also another point. It's not just that you're storing on memory in the RAM, but it's also the memory throughput is significantly less, and most of this should be memory bound, so you're actually running faster.
Exactly. So that's also the point. So if you think this, you have to read for an operator, so you have like a factor of 500 less things to read every time you run through the operator, right? So yeah, so that's definitely it's an advantage. Then you can add all these additional coefficients and parameters, and you're still winning, I guess.
Okay. More questions. Your chance to ask Patrick. Please unmute and ask. I see Joe has raised her hand. Sorry, I'm missing those. Joe, you want to ask the question?
Yeah, thank you. I have a quick question about what you said at some point that for immersed boundary methods for simulating fracture, that you cannot handle blocking fractures. So if the fracture is not conductive, so is there a way around that? Because it seems like fairly constraining for some problems.
Yeah. So the way we handle it in here. The way we handle it in here, and I think probably I'm missing one of the pictures, but we have this, let's say, this code that can handle all sorts of non-conforming things. So if we have a barrier, we just model it differently, and then we have like a superposition of meshes. but all the barriers are modeled inside, let's say, explicitly in the background. I guess if you want to do something different, then maybe an approach like FEM would be probably best than using the approach we're using, which is based on the continuity. So by definition, cannot support this. We also try to see if we add an equidimensional fracture to model the barrier, but it wasn't the case that it works. Was too bad. Kind of reached similar things, but was too bad to be useful.
Thank you.
Okay, thank you, Joe. Other questions? Okay, matrix free, great. But then we have to solve something without a matrix. You mentioned multigrid. Is this geometric multigrid, or can you give us a little bit more detail about the solver, particularly when you have contact?
Yeah, so this at this point in time, it's fully geometric, but we are working. So it's a shared goal that we have is to handle the core spaces with an algebraic multigrid, so we can do the let's say heavy lifting matrix free on the fine levels, and then we can do additional coarsening using algebraic multigrid, and this is why you want to have the flexibility to let's say to have many more elements for the surface description like you have here, but still be able to scale even if the problem is very large. So this is something we're planning. So it will be a hybrid geometric algebraic multigrid in the end.
So this is similar kind of to P multigrid for higher elements, correct?
If you want to do high order, yes, then we have a P multigrid, and then we have a low order refinement. So the plan would be, P multigrid or some kind of low order refinement preconditioner, and then geometric levels on the top, and then algebraic levels on the bottom.
Yeah, but I mean, what you're doing is like P multigrid in the sense that you just use the geometry until you get to the coarse grid.
Yeah.
And you do that all of this matrix free, and then at the coarse grid you assemble into an MG.
Okay. I implemented a P multigrid many years back. I did everything with matrices. So.
No. You're supposed to do it. Yeah. Okay. All right. I get it.
My knowledge, I guess, it's a bit limited to that, but I mean, definitely makes sense to do also that. But I think there is still value to exploit the structure also for low order finite elements, not only for.
And then for the contact, the case of contact, is MG enough? Do you have issues when you have contact?
We're still working on that, yeah. So MG.
Good.
We eventually figure it out. So we have some ideas, but I don't want to spread disinformation. So cool. I guess we'll figure it out. I hope in the next months, and so there are a few ideas, and if this pay off, you will definitely see an article soon.
Good. This is something we're working on too.
Okay. I mean, if you want to join forces on certain things, we'll be happy to do that.